So thank you very much for coming. It is really great to be invited to give a talk at home. So I'm going to take this opportunity to tell you a little bit about my recent and ongoing work, and also to tell you about ideas for future research. So I would like to start by emphasizing the multi-scale nature of galaxy evolution. So on large scales, of course, the universe is expanding, while density perturbations grow by gravitational instability to form these cosmic web of filaments and dark matter halos that you can see here in dark matter density projection from the Millennium simulation. Now, galaxies form at the density peaks at the centers of dark matter halos, which is where gas can cool down and condense and to high enough densities to form stars. And in turn, massive stars can affect the surrounding interstellar medium by different processes that we call stellar feedback. And those include supernovae, radiation, stellar winds, and other processes. And those can affect, they can disrupt the molecular clouds where the stars form at scales much smaller than the galaxy itself. But this process can also affect galaxy evolution as a whole at much larger scales. And then when we move on to the centers of galaxies, we believe that most sufficiently massive galaxies host a supermassive black hole at the center. And in this case, the accretion disk around the black hole is really tiny in size compared to the size of the galaxy, and yet the black hole accretion process can release enough energy to have a very significant impact on galaxy evolution. So it's really a challenging problem to understand how galaxies form in this cosmological context and large-scale structure formation scenario, and then at the same time capturing many of these very important processes that occur at much smaller scales. So the basic ingredients to study galaxy formation are the initial conditions, which are these primordial density fluctuations, which are very well known from cosmic microwave background observations. And then in the context of galaxy evolution, we assume that the background cosmology is known, so we know how much dark energy there is, how much dark matter and baryons. And then there is a lot of physics that we have to add on top of this. First of all, to evolve the dark matter component, just solving gravity, gravitational forces. And then in terms of the baryonic physics, we need to add self-gravitating fluid dynamics, and then many processes such as gas cooling, star formation, and as I mentioned before, a stellar feedback, black hole feedback, and so on. So my favorite technique to attack this problem is cosmological hydrodynamic simulations, which offer a very powerful tool to include many of these processes explicitly, even though, as I'll mention throughout my talk, the simulations require the use of subgrid models, again, to deal with physics occurring below the scale that we can resolve. So let me first motivate the need for feedback in galaxy evolution. So this plot here is showing the stellar mass function for galaxies, which is basically showing the distribution of galaxies in terms of their stellar mass. Here, the black points correspond to observations, RSU 0, this is present-day galaxy stellar mass function. And then the blue points here correspond to the result that we obtain when we run a very simple cosmological hydrodynamic simulation with a reasonable prescription for how gas gets converted into stars, but with very weak stellar feedback or even no feedback at all. And as you see, what we find is that, well, the simulation overproduces the number of galaxies basically at all masses. So star formation is way too effective, and galaxies become overmassive, and this is very well-known result found since many years ago. So now the overall consensus is that for low-mass galaxies, stellar feedback regulates star formation, and perhaps large-scale galactic winds is perhaps the best manifestation of the effects of stellar feedback, which can be produced again by a combination of some of these processes that I have mentioned. And nowadays, we believe that galactic winds are essential in order to regulate star formation in galaxies, but also to explain the metal enrichment of the intergalactic medium. So metals, heavy elements are produced in stars, return to the ISM, and then galactic winds can deposit these metals far from galaxies. Now, what happens is that the stellar feedback is not efficient enough to regulate the star formation in massive galaxies. So in order to stop forming stars at the massive end, we need some sort of additional source of energy. And one very popular candidate for this is black hole feedback. So the accretion process can again generate a huge amount of energy, and in fact, the total energy released from black hole accretion can be a factor of 100 or even 1,000 times the binding energy of the galaxy. So there is in principle more than enough energy to have a very large impact on the host galaxy. And the mechanisms that could play a role here are accretion-driven winds, for example, and jets or intense radiation fields, and so on. So some of these mechanisms might be responsible for catching galaxies at the high mass end. So a lot of my recent work is being done in the context of the FIRE collaboration. This, the FIRE collaboration is now a very large group of people, and I'd like to acknowledge some of my main collaborators. So first of all, Chris Hayward here at the Flatiron Institute at CCA. Then I'd like to highlight the Northwestern University group led by Claude-André Faché-Guiguet. And then some of my other main collaborators are Phil Hawkins from Caltech, Dushan Keres from UC San Diego, and Elliot Pater from UC Berkeley. So very quick recap of the main properties of these simulations. So these are zooming simulations, which means that we focus all of our resolution elements in a small region of the universe where we know that a single galaxy or perhaps a small group of galaxies is going to form. And that way we can have much higher resolution than what we can achieve with a large volume simulation with a uniform resolution. Now, thanks to this increase in resolution, we can do a very detailed job at modeling star formation and stellar feedback. So stars in these simulations only form from very high density gas, only out of molecular, locally self-cavitating gas. And then stellar feedback processes, supernovae, stellar winds, and radiation are injected locally at the scales of star-forming regions. And all of the feedback quantities, including mass return, metals, momentum, and energy, are directly taken from stellar population synthesis models. So this is obviously a very quick recap, but I'll just like to point out that this combination of resolution and physics has been very successful in explaining a wide range of observations. So now the question is, well, this is a success of the model. Obviously, we need to validate the models by comparing to as many galaxy observables as possible. And after we have done that, and of course we identify things that work, things that don't work in the models, we can still ask, well, how do galaxies form? Obviously, galaxy formation, as I've been describing, is a very complicated process. So how do we understand the galaxy formation process? So one technique that I like very much is to look at galaxies at low redshift at the end of the simulation and then follow them back in time to see where the mass comes from, to really decompose the mass assembly of galaxies into the main physical mechanisms. So traditionally, galaxy mass assembly has been studied in terms of, well, what is the contribution to the mass growth of galaxies coming from smooth accretion from the intergalactic medium, and then this gas being converted into stars in this central galaxy that we're looking at, and then what is the contribution from galaxy mergers. And this has been done for many years now, and for example, it is well known that mergers represent a very small contribution to galaxy growth, when we go to the most massive galaxies, where they become very important. Now, thinking about other plausible channels that mass, other possible trajectories that mass can go through before being converted into stars are galactic winds. So we believe that galactic winds can eject substantial amounts of material out of galaxies. So it is plausible that some of these gas can recycle back to galaxies after being blown away, and then forming stars after that. And this is a process that we call wind recycling, and is possibly also very important in galaxy evolution. Now, if we consider winds from this central galaxy that we are studying, we should also consider galactic winds from other galaxies. So the other nearby galaxies, of course, are ejecting mass gassing winds. And here we are going to consider also this different trajectory, which is galactic winds ejected from other galaxies that somehow may end up accreting onto the central galaxy and fueling star formation. So what we did with the FIRE simulations is then track individual mass resolution elements and look at the trajectories of gas and stars as they get to form the central galaxy. So this is now real simulation data, just illustrating the typical trajectories that galactic winds, the gas ejected in galactic winds follow. So this is a dwarf galaxy, a redshift 2 or so, and these stellar symbols illustrate the stellar component of this galaxy. The dashed lines here correspond to the virial radius of this halo. And then the blue lines show the future trajectory of gas that is about to be ejected from the center of this galaxy. So these are gas resolution elements that are identified as being blown out at this particular time, and then we know that that gas will come back to the galaxy and fuel the star formation at a later time.
There must be some very non-trivial reference frame issue here.
So yeah, of course. So this is all the time computing using the center of the galaxy over time as the reference frame, exactly. So yes, it's quite tricky to visualize these particle trajectories, but still they convey what we find in when we quantify, for example, the distance at which galactic winds recycle back, and they do actually reach far beyond the virial radius in some cases, even though most recycling occurs close to the galaxy.
So when you look at the star formation history of these galaxies, is it more in this continuous mode, or should I think of this as a series of bursts where there's a burst, material flows out, future burst?
Very good. Yeah. So very good question. So low mass galaxies, very vastly, we should think of galaxies undergoing one big burst, which will eject a lot of gas. Some of that will come back and then will fuel the next parts of star formation. But then one very interesting prediction from the fire simulations is that when galaxies become big enough, and stellar masses of order of 10 to the 10 solar masses or so, then star formation becomes much smoother, even for the same global star formation, but occurs much more extended. So stellar feedback is less efficient, and then galactic winds are not as strong. And this is quantified, for example, in the evolution or mass dependence of the mass loading factors of galactic winds.
So this picture I should think of as for a galaxy that's still in the bursty mode, driving winds.
Exactly.
So this is 10 to 11 solar mass halo, and what, 10 to the, a few times 10 to the 9 in stars?
Exactly, at redshift 0, and we are looking at this at redshift 2, so this is very small galaxy, very vastly. Exactly. So I'm going to show this type of effects in other galaxies as well, or as a function of redshift. So now, what was most, I think, surprising to us is when we look at galactic winds ejected from nearby galaxies, and then only highlighting the trajectories of gas ejected from other galaxies that then we identify as fueling stars in the central galaxy at a later time. And this is, again, this is obviously a snapshot or a redshift in time chosen to illustrate this behavior, which is a very particular moment in time where this galaxy is undergoing a big burst, and a lot of this gas will end up fueling the central galaxy. So I'll show later that this channel for galaxy growth can actually account for up to 1/3 of the stellar mass of galaxies like the Milky Way. Now, we can do this over time just to illustrate that what I have shown is not just a very specific, very rare event, but this happens over time for the evolution. This is the same dwarf galaxy at redshift 0. So yeah.
How come? Can you go back?
You mean the movie?
Yeah, here, right. No,
Yeah.
That image. Yes.
Yes.
So how come you don't have any tracks going, you know, to the right from that other galaxy? And then why is
Right.
it only gas from like one side of the galaxy?
So exactly. So the actual outflow has been ejected from here are quasi-spherical. So there is a lot of gas also ejected in this direction. But I am here showing only the gas that will end up accreting on this galaxy.
Yeah.
So a lot of this
Yeah.
gas will, for example, recycle back to its own galaxy, or will be lost in the intergalactic medium.
But really, nothing that is blown by a wind to in the other direction will end up in that other galaxy.
So
it's really that the wind is really launched in the direction of the other galaxy.
So the wind that happens to go in the direction of sort of the merging event, it will more likely be accreted onto the central galaxy.
When that is launched in the right direction, gets to it. That's different.
But then, I mean, if you look at some of these trajectories, for example, some of these winds that are ejected here in almost the opposite direction.
I'm just surprised that there's not more like mixing in the halo of this other galaxy that leads to some tracks.
So, I mean, so there is a lot of mixing, and then if we look at the animation, there are all kinds of events happening. But yeah, so it's true that as the galaxy, this halo is merging onto this galaxy, so we have to think this as a continuous flow that is sort of expanding from this galaxy and then this whole thing is going to end up accreting onto the central. Yeah, but this is highlighting only what we identify at this particular time as being ejected, and knowing that in the future it will fill the star formation. So maybe now focusing here, so in some cases, for example, you have seen here outflows going backwards and then ended up accreting. So it depends on a case by case. Now I think it's very interesting also the same type of process, this intergalactic transfer of mass from satellites onto a central galaxy, but now focusing on the regime of the central galaxy, a Milky Way mass galaxy at low redshift, and then tiny satellites orbiting around the central galaxy and providing mass in outflows. So, which is what is illustrated here. So the stellar distribution of the Milky Way mass galaxy is illustrated in the background color scale, and these green points are just gas resolution elements identified. We catch them right at the time when they are leaving, and we can only highlight in gas that we end up fueling a star formation in the central galaxy.
Daniel,
So
in this phase, do the satellites also reaccrete material?
absolutely. So exactly. So they can also reaccrete some of the material. Here we only show the stuff that is not reaccreted. By definition, it will end up in the central. But in this regime, I should clarify that recycling for satellite recycling the low winds is much more difficult because of ramp pressure in the halo. So it's different as when we look at dwarfs, isolated dwarfs. So then we can compute how important are these different channels for galaxy growth. And so here I'm showing the fraction of the stellar mass at redshift 0 for a few different galaxies, increasing in mass from left to right. And then the color here corresponds to the different mechanisms. So purple is fresh accretion, blue is wind recycling from its own galactic winds, green is intergalactic transfer, and then red and orange correspond to mass from mergers from both stars and gas. And so I'm gonna just very quickly highlight that the amount of stellar mass today in Milky Way mass galaxies, which are these three labeled as M12s, the amount of stellar mass today that has been part of an outflow in the past is really like 70% or something like that, which is adding the blue, which is its own wind recycling, and then this intergalactic transfer mode, which can account for about a third or so. So it's really, really very important for galaxy mass assembly. So now, in order to understand how is the galactic winds are so important, then we can look at the efficiency of outflow as quantified by the wind loading factor, which is defined as the mass ejected in outflows divided by the stellar mass formed, which is what I'm showing here, as a function of the stellar mass of the host. And we see this very strong dependence on galaxy mass, where tiny dwarf galaxies can have mass loadings as high as 100, so very, very efficient at ejecting gas compared to converting gas into stars. But then at some point, as I mentioned before, massive galaxies become less efficient at ejecting winds, and this explains this bend in this stellar mass dependence. Now, I'd like to point out there are many other galactic wind properties that we can study, but I would like to just point out that measurements of mass loading factors that are predicted from the 5 simulation in this case can be very useful to incorporate subgrid models for galactic winds in large volume simulations where the resolution is not enough to produce consistently this type of models, and I'll come back to that later. So there are many other things that we can study using this technique of particle tracking, and so Sackhafen, graduate student at Northwestern, is doing a lot of very interesting work on the CGM of galaxies, tracking gas flows to find out what is the origin and fate of CGM gas flows, and this is illustrating some of these gas particle trajectories, depending on their origin, whether it comes from IGM accretion or galactic winds from the central or satellite winds and so on. And there are also very interesting analysis that can be done by incorporating this particle tracking data into visualization tools that allow you to move in a 3D body to understand all of these processes together. One interesting result from Sachs' analysis is that when we compute the CGM mass fraction from the different sources as a function of halo mass, then intergalactic accretion still dominates, but galactic winds from both the central and satellites can represent a significant fraction. And I think as expected, when we look at the metal content of the CGM, then it's clearly dominated by winds, since metals are producing galaxies that need to be pushed out by winds in order to get there. So let me show very quickly, very interesting application of particle tracking, in this case tracking a single star in the simulation. So this is work by Gus Bean together with a stellar team of locals listed here, including Mordecai and Robin, Melissa, and Megan. And so the basic idea is we want to evolve, find the evolution of a star cluster and see how cluster members get disrupted and so on in a realistic galactic tidal potential. So the idea is with one of these 5 simulations, we follow one star particle that will represent the evolution of the open cluster, and then we create a grid along this evolution to measure the accelerations provided from this realistic galactic potential. And then Gus implemented this external tidal potential into a direct n-body solver to follow the evolution of the star cluster. So yeah, I thought this was a very nice illustration of how a combination of techniques, the type of combination of techniques that we need in order to break this barrier of the huge range of scales involved in galaxy formation. Yeah.
So you said these single stars, so each star particle represents individual stars in this kind of simulations?
So each star particle in the 5 cosmological simulation represents a mass, in this case, of about 7,000 solar masses in stars. So we follow one star particle here in order to represent the orbit that potential star cluster to follow. So the n-body, the direct n-body run that is run separate from the cosmological simulation, this represents individual stars, which we would never be able to resolve in the cosmological simulation. So we use the cosmological simulation to get the tidal field from the galaxy.
Okay, so you assume certain initial condition for your open cluster and put it into your external potential provided by.
That's right. Yeah. So there are many other applications. Just quickly, very quickly mentioning that, as many as you know, Robin Sanderson has used 5 simulations in order to produce mock Gaia catalogs with many interesting applications. One of the ideas that we have been discussing is to add or particle tracking pipeline in order to add additional attributes to the mock Gaia catalog so that we can tell whether the star particles form in satellites, in which satellite, at what time they got disrupted, or whether stars that end up in the halo, for example, came from originally forming the central galaxy and somehow got ejected. So I'm going to switch over to black holes now. As I mentioned, black holes potentially very important in galaxy evolution, and they are also very interesting on their own right. So one of my key roles in the 5 simulation is to develop black hole physics. So in the first study where we incorporated models to track black hole growth, we decided to simulate massive galaxies. So these are quasi-host galaxies at redshift 2, and then evolving down to redshift 1. And the focus in this case was to study how stellar feedback affects black hole growth, or how black holes grow in galaxies where we now are able to resolve the multi-phase ISM with much greater detail than what has been possible before. And well, this illustrates the huge dynamic range that the Zoom simulations can accommodate, from sort of virial radius scales to all the way to the central kiloparsec. But still, in the central 100 parsec, we begin to run out of resolution. So we still need to rely on a subgrid model to parameterize how much gas should be feeding the black hole at the end. And we do this by using the gravitational torque accretion model from Phil Hawkins and Elio Poitaer, where the basic idea is that non-axisymmetric perturbations in the stellar potential drive the gas into shocks that dissipate energy and angular momentum. So I'm going to skip over the details of that model. The model is quite complicated, but it makes a very nice prediction in terms of the local inflow rate at a given radial aperture, in terms of the gas mass and dynamical time. And then this depends on the fractional non-asymmetric perturbation to the stellar potential. And they were able to integrate this, knowing from the simulations what were the dominant modes at different scales, to provide a subgrid prescription for inflow rate at subparsec scales as a function of some quantities, including the disk fraction or total gas mass, and also black hole mass and so on, evaluated within a scale of about 100 parsecs or so, which is what we resolved in the 5 simulation. So this is how these galaxies look like when we look at the evolution of the stellar mass surface density, which is shown in the background gray scale here. And then overlay on top of that, you can see the gas mass surface density going from purple to red for very high gas densities. So basically what we see is that, well, at early times galaxies are very bursty, and so stellar feedback really disrupts the center and removes gas very efficiently from the center. But at later times, the nuclear stellar potential is able to retain a substantial gas reservoir, which allows the black hole to grow. And this is now reproducing the same animation, but now on the right you can see the accretion rate of the black hole as a function of redshift, and then on the top panel here you can see the black hole mass as it grows compared to the galaxy stellar mass divided by a factor of 1,000 here. So basically, what we find is that this early bursty behavior makes it very difficult for black holes to grow. So sometimes black holes grow at very high Linton radius, but only during very short periods of time, because then stellar feedback very quickly evacuates gas from the center. And so the black hole at the beginning is growing very little while the galaxy is growing. At some point, this is a feedback and star formation switches behavior when the galaxy becomes big enough, and then accretion begins to be more steady. And this is how this looks like when we look at the black hole mass versus bulge mass relation. So here, the gray band shows observations, the local scaling relation from Hayden and Riggs. And now the color lines show 4 galaxies, and then how the black hole and the galaxy, how they evolve in this black hole mass versus bulge mass plane. So we see this very strong evolution where black holes at the beginning are basically waiting until the galaxies become big enough, and they transition from very bursty and regular, very often not even the galaxy center is well defined at early times, to then very well-defined and deeper stellar potential that can retain nuclear gas reservoir, and this is the regime where then black holes convert into the scaling relation. So this has many important implications, and including, for example, our understanding of the black hole galaxy scaling relation. So this makes strong predictions for black hole masses at the low mass end of the same sigma relation. Interesting implications from the growth of early quasars. So as many of you know, it's very challenging to grow the higher redshift quasars fast enough so that they can reach 10 to the 9 solar masses by redshift 7 or so. So it's very important to include efficient stellar feedback in the regime. And then also this effect can be very relevant for NGM demographics and time variability, and other subjects that are very interesting for some people in the audience, like black hole mergers. Since the galaxy to black hole mass ratio can depend a lot on whether the galaxy is in this regime or in the efficient black hole growth regime. And also important, of course, for black hole feedback. We need black holes to grow efficiently in order to be able to stop star formation in galaxies. So a lot of this is obviously very important, and a lot of people in the galaxy formation community are looking into this. And in particular, Melanie has very nice work also looking at the effects of stellar feedback at early times affecting black holes, and we agree qualitatively on this type of behavior. But there is, of course, still much uncertainty on how we treat black hole growth, and much more work is needed in this direction. So I'm going to switch over to AGM feedback, but before doing that, I'd like to highlight some very interesting work done by Rachel Cochrane, who is a graduate student at the University of Edinburgh, but as many of you know, she was here last summer for the Cadiz School. So she has used the simulation of massive galaxies to then perform 3D continuous relative transfer with SCIRT in order to make detailed comparison to observations, and in particular to 2-millimeter galaxies. These panels here are showing sort of the spatial distribution of intrinsic properties measured from the simulation. So this is the stellar mass, the dense gas, the dust, and then young stars, which basically trace star formation. And then on the right column, you can see the morphology of the galaxy in different wavelengths, going from UV to optical, near infrared, and far infrared. So one very interesting result from this study is that the galaxy has very different morphologies depending on the waveband that you use to observe them. And often, Rachel finds that the UV traces holes in the dust. So basically, regions where the dust column density is too high, then doesn't allow you to see the UV, the young stars, behind them, and the UV only shows up in some cases in regions where there is no dust. And so we are about to submit a paper on this, focusing on the spatial extent of the dust continuum emission, but there is a lot of ongoing work and many ideas for future work, including studies of time variability at different wavelengths. I have rerun some of these galaxies with very high time sampling so that we can really look at time variability as seen through different bands, and that can be, for example, very important to study the duration of bright submillimeter phases, which is still very uncertain. Yes.
Do something like H alpha?
I think we could. Yeah, we haven't done that yet, but it would be interesting. That's why. So we're just beginning to explore sort of to what extent we can make mock observations on this new set of galaxies to make predictions for rest of galaxies.
Well, you don't have photoionization, so you have to do H alpha.
Yeah, that's right. Yeah.
Oh, did you?
So.
Do you have photoionization?
So as part of the stellar feedback models we do, but here, well, I mean, some simple recipe to treat is not, yeah, some simple recipe to treat photoionization. So in this case, we are just basically doing a 3D continuum transfer. So just treating absorption, scattering, and emission from dust. So moving on to black hole feedback, lots of observational evidence for different channels of black hole feedback, but also lots of uncertainty on what are the dominant physical processes generating these different types of feedback, and also how they couple to the surrounding galaxy and whether they are important or not for different aspects of galaxy evolution. So there is currently a lot of developing in the collaboration in order to incorporate some of these different black hole feedback channels. But today I'd like to highlight some work on modeling fast nuclear winds and then modeling how they interact with the surrounding multi-phase ISM. So this is looking at the central 500 parsecs from one of these massive galaxies, where now I will be injecting fast nuclear winds at the scales of about 0.1 parsec around the black hole. These winds will have a velocity of about 30,000 kilometers per second and a mass outflow rate similar to the black hole accretion rate. And these parameters are typical for what is observed as broad absorption line winds. So here, the background gray scale is just the background gas surface density, and the wind. We are injecting new resolution elements in the simulation so that we can see the evolution of galactic winds at much higher resolution compared to the standard resolution in the simulations, and we can also trace the evolution separate from the rest of the gas component. So one interesting result that we find is that even though we are injecting spherically asymmetric outflows, isotropic winds, we see that the ISM can efficiently collimate the winds, so that actually when we look at the gas surface density profile, so for example, the star formation rate surface density as a function of distance from the center, we find that, well, the winds can suppress the star formation at the center, but depending on their energy, the ISM at larger scales may be broadly unperturbed. So it's a very, very important result that we need to allow winds to escape along the polar direction as it would happen in the real universe. So this is still work in preparation, but I think it's very exciting to be able to simultaneously capture the wind ISM interaction very close to the black hole at 10 parsec scales or so in the simulations, but then going all the way up to the scale relevant for the CGM. And so, as I mentioned, we see the formation of a low density, high temperature central cavity, but often the ISM at larger scales is unperturbed. Now, a very important aspect of this project is also a cold comparison between different implementations of galactic winds, and many of you from the Galaxy group know about this work. So this method of wind implementation is very accurate, it's very nice, but it's very expensive. So we need to develop easier or cheaper ways to implement galactic winds in full cosmological simulation. So now what happens is that when you inject the same amount of energy in different ways, the results can be wildly different. So this is now the same galaxy seen in phase on in top row, edge on in the bottom row for different levels of zooming. So this central kiloparsec is shown here in the right panels. And now we inject the same energy, but very different feedback implementation. And as you can see, the results are really, really different. So with the same energy, you can blow up the whole thing. So what is happening? Well, one very important effect is that in this wind implementation, we are doing what is most commonly done until today in cosmological simulations, which is the black hole finds the nearest gas resolution elements and then you kick them out. Now what happens is that in a situation where most of the resolution elements are in the disk of the galaxy, that means that you are coupling the entire AGM feedback energy in the direction of the disk of the galaxy, and you are not allowing energy or momentum to escape along the polar direction, which we think is what should happen in the real universe. So we need to come up with ways to account for this geometric effect, but with models that are cheaper and easier to implement in large volume simulations. Another interesting aspect of this project is I'm applying this very high resolution AGM wind injection in order to see if AGM winds can regulate the central densities in massive galaxies. So this is now the same galaxy, but a higher redshift, so very high densities. So I'm trying to select the galaxy right before it gets really, really compact and see whether different levels of feedback from the central engine can prevent for the central galaxy to reach too high densities. So now I have described many results that can be obtained from very high resolution zooming simulations, but of course they have a major caveat, which is the numbers, the statistics. So we can only simulate a few galaxies, relatively small number of galaxies, very high resolution, but we cannot make statistics. So it's very important to simulate large volume simulations so that we can look at galaxy populations. And of course, it has been done very successfully by a number of different groups, including TNG, of course, which has been as successful as even selling stamps in Germany, which I think is amazing. So anyway, so these simulations that I'm highlighting here, some of them, they use different hydro methods. They use, in general, very different methods to implement the stellar feedback, black hole feedback, and so on. But they all have a key ingredient in common, which is they all use a bond accretion in order to parameterize black hole growth, or in some cases variations, but basically the same bond accretion formulation. Now, this assumes spherically symmetric accretion, which means that angular momentum is explicitly neglected. And in principle, I mean, we know that in gas-rich galaxies, when gas rotation is supported, then it's something that we need to deal with. And something which is particularly important when parameterizing black hole accretion rate is the dependence of the accretion model on black hole mass. And this very strong dependence of bonding on black hole mass has very important implications both at the low black hole mass end and also the high mass end. So the low mass end, this power of two dependence will strongly suppress black hole growth, which has been a headache for many galaxy simulators for a while, which means that you have to either artificially boost accretion by some numbers so that bonding can start growing efficiently, or you have to start with seed masses, which are perhaps more massive than what you ideally would want to have. But then at the high mass end, then the accretion basically diverges by construction owing to this dependence, which means that the black hole has to self-regulate by its own feedback. Otherwise, it will diverge. So this means that the way you model feedback is might be somehow conditioned to the way you are modeling black hole accretion. And in previous work, I have shown that when using gravitational torque accretion model that I have described previously, implemented in cosmological simulations, we don't need black hole feedback to self-regulate their own growth, and we can reproduce the MC-MAR relation basically just based on the efficiency of accretion. So the picture here is that gravitational torque drive inflow rates at a rate which are on average proportional to the star formation rate on the galaxy. So if you tune the normalization of the accretion model, then you are able to reproduce these scaling relations. And then we found that when we further add AGM feedback, even powerful AGM feedback, we still have a very similar relation. So feedback in this case is affecting both black holes and galaxies, but just moving systems down to lower masses, but not changing the slope. Now, when we look at basically every other simulation using bond accretion, in this case, the normalization of the MC-MAR relation is driven by the feedback efficiency. So probably neither of these two accretion models is right, but clearly it's very important to understand how black holes grow, because, for example, just to understand what is the physical driver of the enzymar relation, then we can go from the extreme of being totally independent of the accretion normalization and just depending on the feedback normalization to the opposite, being independent of feedback and basically depending on accretion. So this was one of the motivations for the SIMBA simulations, which are the next generation of the Mufasa simulations, for those of you who might be familiar with this. And this is work in collaboration with Romilda Bey, Desika Narayanan, and students in their groups. So basically, this is an update of Romilda Bey's Mufasa simulation, where the main update is the addition of black hole growth and feedback, but we have implemented also some improvements. And in particular, I'd like to mention that now the mass loading factors that the way we implement galactic winds in SIMBA is using the mass loading factors that I have measured from the fire simulations that I have mentioned previously. Now in terms of black hole growth, we are using the gravitational torque accretion model from Hopkins and Quattair, but only from cold gas, which is where it is supposed to apply. So we have a two-mode black hole accretion model where Bondi can operate only from whole gas, because in the case of whole gas, pressure supported, then spherical accretion, it might make more sense. So that might be a good prescription for the inflow rate towards the black hole in, say, elliptical galaxies where there is only a hot pressure supported gas. But then from cold gas, we allow black hole growth to follow this gravitational torque implementation. And the nice thing is that this gravitational torque model dominates at early times, which allows us to basically reproduce the M-sigma relation or the black hole mass versus batch mass relation, regardless of the way we model feedback. So basically, we have extra freedom in the way to implement feedback, because just the accretion itself is giving us the nice black hole galaxy scaling relations. And this is work from earlier papers where I showed that with this torque accretion model, it doesn't matter whether you start with over massive Cs or under massive Cs, they naturally converge to the scaling relation, and this is mainly driven by the weak dependence of accretion of black hole mass. So, and then of course one of the important additions is a two-mode black hole feedback. So this is in some way similar to TNG, where we inject a kinetic, or we inject kinetic bipolar outflows in both channels, but then we have large mass loading factors and outflow velocities of about 1,000 kilometers per second when black holes are in the relatively efficient regime, so that would be the quasar mode. And then we transition onto a jet mode where we use lower mass loading factors, but we can cut the outflow velocity up to about 8,000 kilometers per second. So the motivation is basically see if we can sort of implement like very high velocity collimated outflows, sort of mimicking large scale jets, while in the relatively efficient regime, having highly mass loaded outflows and seen in molecular outflows. And another addition is a model for dust production, growth, and destruction, where dust is passively advected, which can allow make predictions for a wide range of observations. So the first paper is submitted, and in after pH, we find good agreement with a range of observations, including the galaxy stellar mass function, the star formation main sequence, H1 and H2 fractions, mass metallic relation, and other observables. We also identify a couple of caveats. For example, in the stellar mass function, we still have a slight overproduction of stellar masses at the high mass M, but overall very nice comparison to observations. And there is a lot of ongoing work. So this first study is just testing how this new model works. And there is a lot more going on. And here Daisy, for example, here at the CCA, is using SIMBA in order to model submillimeter line emission from the first galaxies. And I'm very excited about the possibility of adding SIMBA to the simulation comparison of the IQ collaboratory that Giske Starkenburg is running here at the CCA. So I already have my own to-do list for the IQ collaboratory on this. I'll start next week. So very quickly, so this is work in progress, but now we can study black hole growth as driven by these two different channels. So this is showing black hole mass as a function of redshift, and then we find that early growth is clearly dominated by gravitational torque. So this is star-forming galaxies, cold gas, rotationally supported gas. And interestingly, this also corresponds to the period where black holes are accreting at high Linton ratios. So we can make a connection between the fueling mode and also the feedback mode. So that would be quasar mode dominated. But then at later times when the accretion becomes more important, when the galaxy grows and there is more hot gas at the center, and in this regime, black holes are accreting at lower Linton ratios. So the J mode is more important in this regime. Some more very interesting student work. In this case, this is Josh Borrow from Durham. He was also another student in the Kavli school here, and he's doing very interesting analysis of the large scale motions of baryons relative to dark matter. So I don't think I have the time to get into this, but basically you can quantify how much the dark matter moves from the initial conditions to the end just based on gravity and dynamics, and this is basically the distance to which dark matter moves, which is confined to basically 1 megaparsec or so, compared to how much baryons can move owing to feedback, which is really, really different. So we are analyzing this large scale behavior in terms of these distance metrics, and also quantifying how much mass lies in between halos. So let me move on to smog. So the smog collaboration is a giant group of people led by Rachel and Greg here at the CCA, and then involving many of you, as you know. So the goal is to combine the expertise from a wide range of topics, from accretion disks to star formation to galaxies and cosmology, in order to improve our understanding of baryonic physics and maximize the science return of the next generation of cosmological experiments. So I have to, there is obviously a lot going on in the smog. One interesting approach, for example, one common idea is to use high-resolution models in order to motivate Sugri models for lower-resolution models that can deal with large numbers of galaxies. And one way is by connecting cosmological thumb simulations from the FIRE project in this case with semi-analytic models, and try to see if we can calibrate the semi-analytic model to the results found in the FIRE simulations, and also to see if we can use the hydro simulations to motivate improved prescriptions in the semi-analytic model. And this is work led by Viraj Pandya from UC Santa Cruz, and with Rachel, Chris Hayward, and others. But now a project in the Black Hole Working Group, which I co-lead together with Yokwata, something that I'm very excited about is the possibility of increasing the resolution in cosmological hydrodynamic simulations to a level enough that we can see and measure the inflow rates down to 0.1 parsec to really understand how black holes are growing. So the starting point for this project is we use simulations from the FIRE project, and then we basically split the gas resolution elements as they get closer to the black hole so that we can gain resolution. So I'm going to quickly illustrate how this works. So this is the central, this is showing the central 100 parsecs of one of the FIRE simulations, and this is showing the gas surface density, which is, you can see that we are really reaching the resolution limit here, even though this, I should say, this is still quite high resolution for a full cosmological thumbing. Now, when we switch on the particle splitting, then the same central 100 parsec becomes very well resolved, and that here was just a hint of some spiral structure. Here it becomes very, very well resolved, and we see all kinds of solar structure. So this is my advertising slide. So we are zooming in from about a couple of megaparsecs going into the central 10 parsecs. This dashed dotted line here is 1% of the virial radius. The circle here is 10 parsecs, and at the center, the black hole can accrete explicitly gas resolution elements that become gravitationally bound within 0.1 parsecs. So really, this technique is allowing a huge dynamic range to study inflows, outflows, and star formation over the whole range of scales. So I am running a bit late on time. So I'm gonna just mention that, of course, one of the focuses is once we have a measure of the explicit inflow rate down to the black hole with these very high resolution simulations, we can compare this with different prescriptions. So at the end, one of the goals is to understand accretion well enough in different regimes that we can implement better sub-beam models for black hole growth. And this is gonna show dynamically how the splitting occurs. So we are starting again from the original resolution from the 5 simulations, and then as the simulation proceeds, we are splitting the gas resolution elements. And at some point, what it was a not very well resolved vertical structure for the nuclear disk in this particular case, then it becomes highly resolved, and we even see a tiny nuclear gas disk around the black hole. And we find lots of very interesting behavior. For example, sometimes the black hole is just spending time in the center of Hall bubbles and not being able to accrete at all until it manages to catch a gas cloud that flies by very close, and then it reforms disk again, and so on. This is still early times. We're in the process of understanding this better, and I like to highlight again the huge range of spatial scales that we can access through these simulations. So I'm going to conclude by summarizing some of the results that I have shown from the FIRE project. So galactic winds are really, really important for many aspects of galaxy evolution. Then I'd like to highlight this new channel for galaxy growth, which is the intergalactic transfer of baryons between galaxies via galactic winds. And then we also find that stellar feedback is also very important if we care about how black holes grow. Then I have shown some early results from the new SIMBA simulations. We are very excited that for the first time we have a viable large volume simulation where we are parameterizing black hole growth based on this gravitational torque accretion model and with bipolar outflows. And then describe some ongoing work in the SMOG collaboration, where we are pushing towards very, very high resolution experiments to understand better black hole accretion and also black hole feedback. And I'm gonna stop by just saying that there is lots of ongoing work and also lots of possibilities for future work in terms of, for example, tracking massive simulations, or, as I mentioned before, a lot of development of black hole physics in the FIRE simulations for the next generation of FIRE. And then plenty of interesting connections between simulations that deal with different scales. And in particular, we are very interested in trying to go from these very high resolution models to then sort of feed back into like thumbing regime and then large volume regime, which is, as I mentioned, one of the key goals of the SMOG collaboration, and lots of interesting connections to a wide range of observatories in the future. So I'm going to stop here. Thank you very much. I'll be happy to take questions.